Okay, so welcome everybody. It's a pleasure to be here once again. Today we have a speaker, which is Hugo Leroy. Hugo is currently a postdoc at EPFL, where he works in a group of Pablo de los Rios. Today he's going to talk about a project that he developed during his PhD, which he did, funny enough, in the same lab where I did my PhD in Paris, in Orsay in particular, under the supervision of Martin Lenz. So Hugo, the stage is yours.
Thank you very much. Yeah, thanks for the introduction, and thank you for inviting me here. As you said, I'm going to talk about the work I did during my PhD, mainly, and now I'm working at the EPFL. And so we're going to talk about collective deformation modes that promotes fibrous self-assembly in protein-like particles. And I guess that those words might not signify so much to you, so I'm going to try to give you a nice introduction of what I'm talking about. So let's get started with first biological example. So here you can see two pictures of collagen bundles. One is from the knee and the other one is from the hip. And you may notice that those bundles have different widths. And in fact, the material itself, which is made of collagen in both cases, have very different mechanical properties. So there must be, and it's due to this difference of thickness in the bundles. And so there must be a biological mechanism that regulates the size of the bundles. And so if you look at the right-hand side, there's a modeling of the aggregation of collagen fibers that are in fact that have this double twisted shape. And there's in general, geometrical incompatibility with the tight packing of fibers and their double twisted shape. So as you can see, when you try to assemble these fibers, they have to deform to adapt and pack tightly. That creates some stress, and in fact, the color coding you can see here is related to the stress in the bundle. And so the stress actually accumulates as the thickness of the bundle grows, and finally limits the aggregation of this type of bundles. So I'm going to give you another example to show you a little bit the topic exactly we're going to tackle here, and broaden a little bit the topic. So we talked about the specific regulation mechanism, but this accumulation of stress in self-assembled system might be a little bit more general. Here you can see, for example, hemoglobin on the left-hand side. It's healthy hemoglobin that is soluble in the cytoplasm, and on the right-hand side there is this sickle cell anemia hemoglobin, where the hemoglobin for some reason start to aggregate and they create this elongated long fiber. And so what happened in this situation, and it's actually quite general, there are many proteins that aggregate and form fibers for many different reasons, but most likely those pathological aggregation of proteins, these proteins are not supposed to aggregate. So they are not, their shape is not designed to fit well into each other, and most likely when they aggregate, that creates stress in the structure that also determine its structure. Could be the width, for instance, of the fiber, or also only the elongated shape. So this type of mechanism of stress that accumulates in upon the assembly has been already studied before by Martin, my supervisor, and the idea they developed is to model proteins using simple geometrical shapes. So you can see on the left-hand side regular hexagon that are actually that is a shape that can completely tile the plane, and you must imagine that it is a very special case. Most shapes do not tie the plane nicely like a regular hexagon, and most shapes are like this irregular hexagon, which has a long side and a short side. And if you try to tight pack all of this hexagon, at some point you will have to match the long side with a short side, and that requires to deform the aggregates once again. So adding short range attractive interaction to drive the aggregation of this type of particle, you may distinguish two obvious regime, one where the particles are extremely stiff, hard to deform, or if the surface tension is extremely low, where this particle essentially aggregate forming tree-like aggregates, and on the other hand, where surface tension is extremely high, or the particle are very soft, you would create sort of a bulk. What I call a bulk is an infinite size aggregate where nothing actually really limits the aggregation. And what they showed previously is that the fibers appears as an interesting compromise between surface tension and and stress accumulated by the aggregation. So that's an interesting study already, but what is missing, what we're missing in this type of model is a link between the mechanical properties of individual particles and the resulting aggregate they would form. So that if you give me particles and ask me what is going to be what happens if they aggregate together, I can tell you that's going to be a fiber, that's going to be a torus, well, that's going to be, you know, infinite spherical aggregate. So that's exactly the question we're going to try to tackle here, to try to determine the mechanical properties, the relevant mechanical properties of assembling particles that will determine the resulting structure of an aggregate. So to do so, I'm going to start by introducing a simple spring model of ill-fitting hexagonal particle. We'll see why they are hexagonal, by the way. And we will see how we can write equation about this, how we can solve a little bit the system, and we'll see. I'm going to try to show you that there is some finite size assembly that emerged, which is already not something especially trivial, and see how we can control the overall structure or the architecture of the aggregates with by tuning the mechanical property of the particles. And finally, I'm going to try to convince you that everything that I'm saying is not so much of a model-specific ideas, and I'm going to use a last model, which is a model of particles with random mechanical properties. So I'm going to try to expand a little bit the previous results, the result of the part 2 and 3. So let's get started with some model more intuitive, the spring model of ill-fitting particles. So we're using this hexagonal type of shape, and as before, I was saying there is a specific case of shape that tile the planes. In fact, if you consider regular shape, threefold symmetric regular shape that tile the plane, there are only two of them. That's the regular hexagon and the regular triangle. And so here I'm going to talk about results related to an hexagonal shape, but what we did for the hexagons is completely reproducible with the triangle, and I mean we actually did it, and it gives essentially the same type of result. So we start with a regular hexagon and moved slightly inward and outward the nodes of the hexagon to obtain a shape that is a little bit distorted. And that keeps this threefold symmetry. The point of the threefold symmetry is mainly to give the opportunity of the aggregate to break the symmetry, creating it eventually fibers or something different upon aggregation, and that the symmetry is not broken at the size of the particle itself. So then we are adding an elasticity to this particle, and so each line that you can see here that I'm representing is spring, a simple linear spring. And so if we try to pack this particle together, we fix the orientation. So we imagine that there is a specific interaction that forces these particles to aggregate in a specific direction. And as you can see, that requires the particle to deform. That is due to the small distortion we introduced at the beginning. And so if I'm creating a large aggregate of such a particle, let's say an infinite bulk, for example, what we obtain is that the only way for these particles to assemble together in a very large aggregate is to become a regular hexagon. And thus this configuration of regular hexagon define an upper bound of the deformation that those particles can undergo upon aggregation. So now I'm going to introduce you a little bit of how we deal with this model, what kind of equation we can write on it. And let's start by just changing a little bit the point of view of the picture we're having here, because instead of, so here you can see hexagons and and if you look carefully, there is two triangular network inside the hexagons. And if I change a little bit the perspective, what we see is that there is two triangular network, a red one and a grid one. Due to the distortion we introduced at the beginning, the red one has a different mesh size. It's slightly smaller than the green one, but they are incompatible, but they are coupled with the blue spring. And this coupling creates stress inside the structure. So from this picture, what we can do is jump to the continuum limit of this picture, where we would have two elastic sheets that are coupled with one another with a continuous coupling. Here, the coupling is symbolized by small lines that if it were discrete, but it's in mind, we should keep in mind that it's a continuous coupling between the two elastic sheets. And what we can do with this continuum model is actually write a fairly simple elastic energy. So that's my only equation of this talk. It looks like a crazy elastic energy, but if you look carefully, it's quite simple. On the first line, the two first terms are the elastic energy of the upper sheet and lower sheet. So it's the regular energy with lambda and mu, the Lamy coefficient that they uniquely define the mechanical properties of this isotropic elastic sheet. And U is the strain tensor. Then there is the coupling energy that couple one point in the lower sheet to another point to the upper sheet with like a quadratic coupling, with kappa being the stiffness of this coupling. And finally, there is just a surface tension that is proportional to the free area of the aggregate. So the reason I'm showing you this equation is to tell you that it is actually a very difficult problem to solve, not only because there's a lot of thing on the equation, but because the real question we are asking is, so if to find the optimal aggregate, what we need to do is minimize its energy not only to the strain field in the system, but also to the shape, which means to the boundary of the integration. And that makes this problem extremely difficult to solve, not to say impossible to solve brute force. So what I'm going to do now is try to show you different technique we use to try to find insight for what is actually the optimal aggregate we can create with this type of system. And so starting with a simple thing we can do is compute the energy of simple shapes. And here you can see the energy of disk for different radius. So as a function of the radius, yes. And for different value of gamma, the surface tension. And what we can see emerging is that there is there is finite size, equilibrium finite size aggregate that emerge from the system, which means that the energy is minimum at like a specific shape. And it's quite remarkable because I did not introduce any length scale a priori, and so there is a length scale that emerged from our system. So let's see what happened exactly, and what we can do is simulate the same system. So that was analytical result, and we can also, on the other hand, simulate the system and see what happens to each single particle to try to find insight on what happened to this aggregate and what stabilized finite size aggregation. And so we compute the equilibrium configuration of different aggregates. That's the equivalent of a disk in the discrete version. And the color coding is related to the stress inside the structure. And what we can see is first that the stress is higher in the middle of the aggregate. And in fact, when the aggregate is very large, the particles, as I explained before, are in this bulk configuration. They are regular hexagon. But we also notice, so the stress decays at the boundary. And there is a boundary layer during which along which the stress decay. And this layer has a length scale that is independent on the size of the aggregate that I'm considering. So here is the length scale that is emerging from our system. That's this boundary layer of stress relaxation that stabilizes the assembly of our aggregate. And in fact, if we have a closer look to this system, we can plot the elastic energy of the individual particle as a function of its distance from the boundary. And as you can see, it increases up to maximum value, which is the bulk energy. And it's an exponential increase with a characteristic length scale that I'm calling here L. And what the continuum limits model is telling you is that I can write this characteristic length scale as a function of the mechanical parameter of my system, the mechanical parameter of my two elastic sheet, lambda and mu, and the stiffness of the coupling. And in fact, the coupling is defined a mode of deformation that allow the stress to relax. And the softer is this mode of relaxation, this mode of deformation, the larger it's going to be L, and the larger is going to be the size of my equilibrium finite size aggregate. So that's the first take-home message I would like to give here, is that this frustration mechanism, this buildup of stress upon aggregation, can stabilize finite size aggregation through this emergence of a boundary layer where the stress is allowed to relax. And moreover, what we've seen, and I've not written in this take-home message, is that there is a mode of deformation that enhance the size, and the softer is this mode of deformation, the larger is going to be this length. And I'm doing a small parenthesis because this thing is something that is already quite known in a different topic, which is the transmission of allosteric message, where here I'm giving the example of the mediator complex, which is a huge complex of many proteins. And what happens is you can have the binding of an activating factor that will trigger a conformational change, that will trigger a conformational change that will spread all along the complex and change the conformation of a proteins very far from where the activating factor bounded before, and will increase the affinity with something else, and thus help regulate some biological process. And so it is the big question of this of allostery is usually what are the mechanical properties of the different proteins that we have to tune in order for this message to propagate at such a large scale. And some people have started to see that the softness, this deformation field propagates along the softest parts of the different proteins. And here we see something very similar, where we have the size of a system that is regulated by some softness of mode, and it reminds a lot about this allosteric pathway that all, and we don't even need more biological ingredient to regulate the size of a system. It just does it by itself, such the same way these collagen fibrils are doing. So now I would like to discuss something, to go a little further in our model and see how we can control the structure of our aggregate, not just the size of our aggregate. Sorry. So I can expand I can use different structure and compute the energy, different simple structure than the disk I used before. And there are not so many structures that can compute. I'm not going to make an extended list of those. But for instance, I can compute the energy of a fiber. That is the other thing that interests me a lot. And I can compare the energy of the disk and the fiber as a function of their width and radius. And most importantly, I can compare so you can see that first of all, there's equilibrium fiber that emerge, but here the fibers are less favorable than the disk. But maybe in another regime, I can find value of the mechanical parameter that will favor the formation of fiber. So what we do is we compare the energy of the best fiber, the best disk, and the bulk for many different values of the mechanical parameter. And so by doing so, we plot a whole phase diagram where the different structure considered have a region of stability. And what we can see on this phase diagram is, first of all, there are two important parameters. The first one is the surface tension, and that's quite obvious. I mean, we knew that before. And the second point is that the parameter, the mechanical parameter that is important to distinguish whether we're going to form a disk or a fiber is the Poisson ratio. And the Poisson ratio is related to how compressible is a particle. So that's the Poisson ratio of the different coupled elastic sheets. So you can see that, so as I increase the surface tension, the size of my equilibrium aggregate increase, whether it's fiber or disk, that's normal, we knew that. And then at some point, when the surface tension is too high, I obtain an infinite bulk. That's something we also kind of knew, but now we know that, particles that are incompressible have the tendency of forming more fibrous-like aggregate. So this is for the continuum model, and what we can do is do the exact same procedure with the particle model, where we design equivalent of disk, equivalent of fiber, and bulk, and compare the different energy. So there are several remarks I want to do about this. First, there is an extra aggregate that turns out to be favorable. That's the so-called Leichner bulk here. So it's quite subtle to see, but in fact, I don't need to deform the particle in order to create this Leichner bulk. It's the best way I can. They all match together. It's hard to see by eyes, but it's basically unfrustrated, and that's the most favorable unfrustrated aggregate that I can create. And the second thing that I think is important on this phase diagram is that if you look, I'm just going to switch between the first and second phase diagram, you see that the fiber region is actually much larger in the case of the particle system. And one of the what we think is that one of the reasons for that is you may notice that the fiber that I'm presenting on the left-hand side are bent, and the bending of the fiber is due to the fact that if the particle, the individual particles, they are threefold symmetric, but they don't have left-right symmetry, and so that creates this bending, and the bending actually turns out to be an additional mode of deformation. That's a collective mode of deformation that stabilizes even more fibers, and it's only accessible to fibers. The disk cannot do such a deformation, and the bulk, and neither the bulk. So it seems that the fiber overall offer more freedom to different mode of deformation than the one I explained before with this characteristic boundary relaxation scale. But overall, I think what is also important to notice is that the tendency with the Poisson ratio is very well conserved. So now we have this interesting suggestion. I'm just doing also a small parenthesis because the method we use here is just comparing the energy of different ansatz of shape that we pre-design, and we would like to we wanted to do some extra testing, and the extra testing we did with this particle model is to use Monte Carlo simulated annealing. And so the idea of Monte Carlo simulated annealing is to perform Monte Carlo simulation where there are particles in a box, and as the as the simulation goes, I decrease the temperature, and as I decrease the temperature, the energy of the system decreases also, and thus creating this aggregation. And so this method is a usual method, optimization method that is and supposedly if I decrease the temperature slowly enough, I'm guaranteed to converge toward the ground state of my system. Then obviously, obviously it's not that obvious, but I never decrease the temperature slowly enough, and especially because we are limited by computation time and many other things. But what we hope to find, what we find with this optimization procedure is an unbiased way, an unbiased approximation of the ground state of our system that we can compare then with the ansatz previously used. So that's what we did, and I'm just showing you a few snapshots of the final equilibrated system. And as you can see, the main feature of the phase diagram is still conserved, where we obtain a disk at low Poisson ratio with size that increases with the surface tension. And same for the fibers. So first we obtain fibers at high Poisson ratio, and well, who knows if the width really increases or not, but it seems that it starts to increase a little bit at the beginning. So of course the results are not perfect in perfect accordance, and one of the reasons for that is that Monte Carlo simulated annealing, and especially in this case where we have to compute to equilibrate we equilibrate the elastic energy of our aggregate at each time step. There's something like a million of time steps for this for the equilibration of the disk, for instance. And the elastic equilibration is a very expensive method because the elastic interaction of particle is a long-range interaction. So it's very hard to have way more particles and to increase a lot the equilibrium time step. But yeah, my first conclusion is that the main features are well conserved. So I hope I convince you about the role of this incompressibility of the particles. That is the second take-home message, because it seems that we have identified a second feature of the particle that will influence the aggregate structure. Because if I did not convince you, it's fine. I have a fourth section that is supposed to be a generalization of what I did before. And first, I would like to introduce you how we generated particles with random mechanical properties, and we then checked the previous observation we did. So that's a little bit of the technical question, let's say. We use particles with similar shape than before, this hexagonal shape that is a little ill-fitting due to this small quantity, small distortion of the order of epsilon. And what we do is, so if I have such an hexagon and I want to write general elastic energy, I have, so there is 6 nodes to this hexagon that defines the degrees of freedom of my hexagon. So there, sorry, there's 6 nodes, so there is 12 degrees of freedom. But if I want to write an elastic energy, for this energy to be an elastic free energy, it has to be invariant over 2 translation and 1 rotation, because it doesn't make sense that the elastic energy change if I move my object. And so I end up with 9 free degrees of freedom to obtain an isostatic system. And to encode these 3 invariants inside our definition of the energy, we use 9 lengths as representation of the 9 degrees of freedom of our system. So you can see the lengths represented here. And if I write the most general elastic energy around a rest state, that is the state L0, I can expand it. I can do a second order expansion of this energy, and that's the form of the equation 2 is the form of the elastic energy obtained. And the important parameter here is MC, the coupling matrix that couple the different degrees of freedom with one another. And to draw a random elastic energy, we'll draw a random matrix. We impose this matrix to be positive definite to force the elastic energy to be stable, as well as that creates an unstable system. And we keep the threefold symmetry of the particles. So notice that any elastic energy can be represented in such a way, and that this matrix uniquely define a free energy. And there's something else I wanted to say about this. I guess it's fine. You can ask question if you see what I missed. So that's how we create our elastic energy, and then what we do is we're going to create the same type of aggregate that we did before and try to see if there is finite size aggregation emerging the same way than before. And to do so, what we need is a generalization of the previous observation we did, because previously, for instance, we had this characteristic lengths that characterize the relaxation of the stress at the boundary of an aggregate. And I wrote the formula that we derived in the continuum module that is related to the coupling spring and the 2 Lamé coefficient. But now we don't have coupling spring anymore, so it doesn't make sense anymore. So instead, to measure this characteristic length, we use the definition of, we use the decay of the stress along. So you can see we create these small strips of particles with transverse periodic condition, and we measure the stress. So we simulate a random particle like this, a strip of random particle like this, and we measure the stress, the decay of the stress at the boundary, and that gives us a measure of the characteristic length of those particles. And what we can do is similar than before. We compute the energy of disks, of random particle disks of different size, and we pick the preferred size as a function of gamma, the surface tension of our system. And we do the same for fibers. And as you can see, that creates this kind of shape. And what is quite remarkable is that I mean, all the random particles, they may have very weird mechanical properties, as we will see later. But despite this, they fall in the same set of curve. And moreover, quite remarkably, the continuum model still kind of works in the system. So, sorry, I just want to emphasize something. The key for this, for the continuum model to match with the random particle and those curves to appear to collapse nicely together, is the rescaling of the radius with the characteristic length, or the rescaling of the width with the characteristic length. And that's what creates this this collapsing. So that suggests that our definition of the characteristic length is the correct one to account for equilibrium aggregation, irrespective of the details of the mechanical properties of the particle. So if you give me any type of proteins and I'm able to measure this decay of the stress, then we're able to understand exactly what kind of equilibrium aggregate it forms. Then sadly, experimentally, it's the inverse that is easier to measure than, I mean, no one measures the stress of a proteins, but still help us to understand. Then there's the other take-home message that I wanted to verify with this random particles. And to do so, I need to introduce a slightly different measure of the Poisson ratio, because as you remember, we had in the continuum model 2 elastic sheets. I hope you remember. And what were important is the Poisson ratio of each of the elastic sheets. And it turns out that in the spring model, the Poisson ratio of the particle correspond to the Poisson ratio of this elastic sheet. So that was very convenient, but it's not the case anymore for this random particle model. So instead, what we're doing is we look at a large aggregate of random particles, and that define this hexagonal lattice. And an hexagonal lattice can also define 2 triangular lattices. So on purpose, I'm not drawing any line between this lattice, because it's just a lattice that is defined by the nodes, and there is no springs in between those lines, but still effectively I can distinguish these 2 sublattices of degrees of freedom, and I can even isolate them one from one another. And so then I can probe the mechanical properties of each of those lattices. That is obviously completely linked to the mechanical properties of the particles. And what I'm going to do is measure the Poisson ratio of each of these sublattices. And then what we establish is that what we're going to call the Poisson ratio of the particle is going to be of the random particle is going to be the average of the 2 Poisson ratio we measure for each of these lattices that are not identical anymore. And so what we obtain is a bunch. So when we draw particles, we draw random matrix and we can measure the Poisson ratio. And here I'm showing you just to show you how bizarre can be those particles. We obtain a whole distribution of Poisson ratio and a distribution of characteristic lengths. And as you can see, especially for the Poisson ratio, there is oxalic particles with negative Poisson ratio. So negative Poisson ratio means if I pull the particle on one side, it blow on the other side, and it's a very counterintuitive situation. It does exist in reality, so it's not that strange, but it's not so common. And we're happy to have random particles that exhibit such a wide variety of Poisson ratio, for instance. And then using this this measure of the Poisson ratio, I can look again about on the stability of this particle and the preferred aggregate they are forming. So what I'm doing here, there's over 1,000 of different particles, and for each particles, I look at the equilibrium aggregates using this by comparing the energy of these different ansatz and increase the surface tension slowly. And what we can see is you see the same feature at very low surface tension. We have the black region that corresponds to the lacunar bulk and frustrated bulk, and then slowly it creates some finite size aggregate equilibrium aggregate. And then there's I just stop at the end where there is some purple which correspond to the infinite bulk. And I sort all of this. So each particle is a single line, and then I sort each of this particle with the Poisson ratio. And as you can see, this definition of the Poisson ratio that we built just previously helps to understand whether the particle will have this tendency of creating a fiber or a disk. Here again, the fibers seems to be there seems to be more fibers than bulks overall, and I think that might be a general feature that fibers offer more freedom. But still, the main point is that the Poisson ratio still high Poisson ratio still favors the formation of fibers. And I'm just gonna finish with this. I mean, I'm not finished this argument with this last graph, where actually the first thing you have to look is the right-hand side, where we plot the percentage of disk as a function of the Poisson ratio, and as you can see, it's less and less likely to create a disk as the Poisson ratio increases. And there's two lines, the green line and the gray line, and we represent what happens when we vary gamma on the left-hand side. So let's say that the right-hand side is the integrated along gamma equivalence of the figure of the left-hand side. So that's the last point to confirm that we still have this influence of the Poisson ratio. So with this, I'm just going to conclude quickly with the idea we tried to develop here, because at the beginning I told you that I wanted to draw a link between the mechanical properties of the individual particles and the structure of the resulting aggregate. And it turns out that it's quite a subtle task, because we want a general features, which means that I'm going to use this particle or that particle, random, not random, or a real proteins, and I want to be able to say something general about it. But on the other hand, I'm going to be interested in some very specific mode of deformation. And here, for instance, I exaggerated a little bit the deformation that happens to a free particle when it enters into a bulk. And as you can see, the volume, for instance, of the area of the green triangle or red triangle is changing, but not so much the area of the blue triangle. And you may have wondered, why didn't you use just the normal definition of the Poisson ratio of the particle? It's because when you assemble these particles inside a bulk, the green area basically doesn't change, and so the Poisson ratio that doesn't matter at all, and only the Poisson ratio of the inner triangle does matter. So what does it tell us? It tells us that it is in fact because I tried to create this random mechanical proteins. This particles with random mechanical properties, but I kept the same shape, and in fact the shape determined the mode of deformation that is going to be responsible for whether we're going to form a fiber or a disk. And so if I don't know anything about the specific mode of deformation of my particle that is responsible for this or that aggregate, I can't tell you what's going to be the mechanical property that matters. So it's quite difficult to have a process, a mechanism that is general but works for every specific particles. So let's say we did half of the job. We especially for the Poisson ratio, where we found a specific mechanism that works for one shape. That's it. And with this, I'm just gonna thank you, and I hope that I got my message delivered. Thanks.
Thank you for this great talk. It was really, really interesting.